I want to talk about the stereochemistry of the SN1 mechanism. With the SN2 mechanism, we always have inversion because that reaction is stereospecific because of the way the substrate has to be attacked. With SN1, what we're going to end up with, let's just go ahead and do a specific example here. Put something with a simple leaving group, and then maybe our nucleophile might be water or something like that. Okay, so this is our kind of overall reaction that I'm drawing here. And what I'm going to do is go in and work through the mechanism of this reaction. So one of the things we can do here to kind of help ourselves out to make this a little bit easier is if we want to redraw this with abbreviations for these groups that are attached to this carbon, we can do that. But notice that we were given a single stereoisomer. So we do not want to change from the single stereoisomer that we were given. But we can use PR for propyl, ET for methyl, and ME for methyl. Excuse me, ET for ethyl and ME for methyl. So now we're going to do the first step of the mechanism, which is heterolysis. We don't need to do any sort of proton transfer here because we have chlorine, which is going to be a good leaving group as it is. So when that chloride anion leaves, we're left with a carbon atom that's positively charged and only has 3 things bound to it. So that's going to be trigonal planar. And if we think about what's happening here, this is sp2 hybridized. Trigonal planar. We know that with an sp2 hybridized atom, we have an empty unhybridized p orbital. An unhybridized p orbital. Sometimes with sp2, that's involved in pi bonding, but in this instance, it's going to be empty and above and below the plane of the trigonal plane. So what can happen here is when we have the nucleophile, it can attack either of these lobes, basically. So it can attack this way, or it can attack this way. And when that happens, with this particular substrate, because this was a chiral compound to begin with, we could have assigned R, we could have assigned R or S to this, because this is a chirality center. We're going to end up with a chiral molecule as a product here, as long as we're not putting a methyl, a propyl, or an ethyl group on here. So I'm going to draw both of the products that we get. So if the carbon attacks, if the water attacks from the right side here, we're going to end up with the water to the right. The methyl down here, the ethyl here, and the propyl here. Okay? And if it attacks from the left, we'll end up with the water on the left. The propyl will now be to the right. And then the ethyl and the methyl will sort of be pushed to the right a little bit. But they'll, of course, still be forward and back as they were. Okay, so now we're looking at this, and it's a little unusual because this is a charged species. But these are actually, if you examine them, these are going to be mirror images of each other, and these are going to be enantiomers of each other. Now, since we have a neutral nucleophile here, we still have one more step in the process. We need to get rid of this extra proton on the oxygen to make it a neutral species. So I'm just going to demonstrate this on one of these, but we'll have another water molecule come in and act as the base to grab the proton off. So when we do that with both of these substrate, or with both of these products, we're going to end up with, and I'm going to switch back to the bond line structures here because that's always going to be our preferred way of drawing things. So that'll be one product, and then the other product will be this one. And again, these are going to be enantiomers. And because there's no reason that the right or the left side should be favored in terms of the attack, we're going to end up with approximately 50% of this enantiomer and 50% of this enantiomer. And of course, we could go in and we could assign RS to this. We know how to do that already. And because this is 50-50 mixture of two enantiomers, this is going to be what's called a racemic mixture. And this, if we were to put this in a polarimeter, we would have half of the solution rotating the light one direction and the other half rotating the other direction. And the specific rotation would be 0 degrees. So this would be not optically active or optically inactive, or however you want to say it. The other thing I want to address here is a little bit of terminology. So typically, when the nucleophile ends up on the same side as the leaving group was, that's going to be called the retention product, because the stereochemistry is retained. And when the nucleophile ends up on the opposite side of the compound from the leaving group, that's going to be the inversion product. And sometimes retention will have the same letter RS as the original, but it'll depend upon what the nucleophile is and how it's ranked versus the leaving group. So I just like to focus on retention is where the nucleophile is on the same side as the leaving group, and the inversion is where the nucleophile is on the opposite side. With SN2, we always get inversion. With SN1, we're going to get this 50-50 mixture of the two enantiomers. And this is one of the ways that you can tell that a reaction is SN1. So if the products are racemic, then you know it's an SN1 reaction if it's a substitution reaction. And vice versa. So if you know it's an SN1 reaction, then you know you're going to get racemic products.